This presentation is delivered by the Stanford Center for Professional Development.
Alrighty, so today's the day when we lift the covers on the machine. It's actually when we sort of like rip open your computer, although I'm not going to rip open a computer. I consider doing that. But we're going to rip open your computer and look at what's inside. And it's really, really small, so you have to bear with me. Okay? But what we're going to talk about is memory. And after today, you will be experts in memory. You'll just be like, hey, Maron, I might not be able to remember anything, but I know all about the memory of my computer, which is the important memory to actually think about. So the first thing in memory that we want to think about, right, when we talk about memory, some people have heard the term like RAM for random access memory. And so like you buy some new computer and you got, oh, I got like 2 gigs of RAM in my computer, right? This is what we're going to be talking about, is what that RAM in your computer actually means, okay, and how it relates to your Java programs and why it's all important. So the very basic notion, the very simplest concept of memory inside the computer is something that's called a bit. And all a bit is, it's actually shorthand for a binary digit. So if you take binary digit and you squeeze it together real hard, also the extraneous letters pop out and you get bit. Okay? And this is just a 0 or a 1. It is a single binary digit, binary being base 2 numbers, which means there's only zeros and ones as digits in that number system. Okay? And that's the simplest kind of thing. So somewhere inside your computer, there's actually like a little piece of silicon or whatever, a little transistor that can keep track of a 0 or 1. So when you get, we won't go below the transistor level. If you're really interested in that, take like, an EE class. But the bit is a 0 or 1. And then we take a whole bunch of bits and we stick them together into something called a byte. And you're like, oh, that whole term like gigabytes. Yeah, that's what it's all about. What a byte is 8 bits. Okay? So basically 8 binary digits strung together is 1 byte. Okay? That's all it is. Now, 1 byte of memory would not be very interesting, right? It's like, oh, I could have one really small number in my computer, right? Because 8 bits can represent like an integer between 0 and 255. It's not very exciting if that's all the memory you had in your computer. So when we think about bits and bytes, we also like to think about larger pieces. There's a piece sometimes people refer to as a word, which actually has nothing to do with English words. But a word is generally the size of what an integer is used to store in some particular language. And it turns out an integer in Java is 4 bytes of memory. So it's 32 bits. 32 ones and zeros comprise the space that your computer actually sets aside for a single integer in memory, which is why an integer has some bounded size, right? You can't just have a number very close to infinity in an integer because it just has some finite size that turns out to be 4 bytes. And that's something that sometimes people refer to as a word. We won't use the word word very much, but just so you know. What we will talk a lot about are bytes. And so bytes, there's a lot of terms related to bytes that you've probably heard. So how many people have heard of a K or a kilobyte? Right? Hopefully a lot of people. And you would like to think the metric system, right? Kilo means what in the metric system? 1,000, right? So you would like to think a kilobyte is 1,000 bytes. But no, computer scientists come along and they're like, no. That's much too round and we're not decimal people. We're binary people. And the closest number to 1,000 in binary is 2 to the 10th, which is equal to 1,024. So a kilobyte, 1K, when you talk to a person who's actually a computer scientist or someone who's putting the RAM together for your machine, you actually sort of get a little extra, right? It's kind of like that, oh, I got some bonus RAM. And like this whole time you didn't even know. They were just giving it to you for free, right? And so there's this notion of a meg, right? Like a megabyte. And a megabyte is basically just 1,000 kilobytes. As a matter of fact, it's not just 1,000 kilobytes, it's 1,024 kilobytes. Because we do everything in powers of 2, so it's actually 2 to the 20th. And then there's probably something you've heard of called a gig or a gigabyte, right? These are the common ones. This 1,024 meg. So when you start adding these all together, right, you're actually sort of getting a lot of bonus memory for your gig. Because it turns out you're getting 124 megs, and each one of your megs is getting 124K, and each one of your K is getting 1,024. So you're getting a little bit of a bonus. So now, it's time for the advanced course. You're like, yeah, Maron, I got so much RAM in my computer. I got gigs and gigs. And so then I would say, oh, yeah, really? You got 1,024 gigs? Because what would that be if that's what you had? Terabyte. Right, so the next one is a terabyte. What comes after terabyte? Petabyte. Yeah, now we're getting into dangerous territory. So each one of these is a factor of 1,024 greater than the next one. Right, what comes after petabyte? Exabyte. There's a few folks. We'll see how long we keep you. What comes after exabyte? Anyone? Zettabyte. With 2 T's, not to be confused with Catherine Zeta-Jones. That's an entirely different zettabyte. So this is a zettabyte, all right? I know, it's just horrible, isn't it? And then after zeta, just to drive the point home, is a yottabyte. I always like to think of it as like a Yoda byte, right? It's just like so much information, you can't even conceive of it. But it's a yottabyte. Like, oh yeah, that's a yacht a good time. We're just not even close to this. Okay? A couple things if you just want to think of orders of magnitude, just so you have some vague idea. If you took the printed collection in the US Library of Congress, that's roughly equivalent to about 10 terabytes is all the printed material, if you thought of each character being represented by 1 byte. Okay? And you're like, oh, that's interesting. If you took all printed material ever, that's about 200 petabytes. So at this point, we're getting pretty close. Like you can go down to Fry's, right, or some other place. I shouldn't name a particular manufacturer or a particular vendor. And you can probably buy about a terabyte of storage, I shouldn't say relatively cheaply, but for a couple $100. Okay? And you kind of crank that up, and you can imagine someone for a couple $100,000 could have a petabyte, right? And then you sort of have a couple $1 million, and you could have enough storage to store all the printed matter ever, right? Which is not that far away. And then, I don't know how someone came up with this number, but I actually found this number, and I was like, how do you measure that? Which is if you took the amount of storage that would be required to store all words ever spoken by human beings. Right? Like, where did they get that number? And it's increasing right now, right? They estimate that would be about 5 exabytes. Right? So we're still sort of in this range, right? Like, yeah, Catherine, she's safe. And the little Jedi guy, yeah, we're not even close, all right? So we still got a lot more information to produce someday. And you're like, oh, I can do that now with my program. I can just have an infinite loop, and I can generate this. It'll still take a while, all right? But it's interesting, just the amount of information that we're actually producing. Now, when we think about actually storing all this stuff inside a computer, so now that you've got some notion of kind of orders of magnitude for these things and what these little bits and bytes really are, the other thing that we want to think about is what kind of representations do we have when we actually store this stuff. So it turns out because we like to think in binary, right? We have bits, which are binary digits. Sometimes it's easier for us to think not just in terms of all the ones and zeros themselves, but some other base system that's easier to keep track of. And so one you might think of is octal, which is base 8 numbers, right? So remember when we did the little ASCII chart and I showed that to you in octal and I was like, oh, these are base 8 numbers, like the digits go between 0 and 7. Yeah, that was octal. That's something that some computer scientists do, but most computer scientists at some point in their life, as a matter of fact, I would say all of them at some point in their life, and now is that point in your life, will deal with something called hexadecimal. And hexadecimal, hex being 6, demical. Yeah, it's hexacomical. Hexadecimal, 6, and then deci being 10 is base 16. We put the 6 and the 10 together. You're like, shouldn't that be 60? No, it's 16. We add. So this is base 16 numbers. And you might say, but Meron, yeah, like I remember these 3, 4, 5, 6, 7, 8, 9. And those were all fun. And like when you told me about binary, I was like, yeah, it was just these two. And when you told me about octal, you were like, yeah, cut here. Now you're telling me about base 16. I got no more digits. Where are my other digits coming from? And you're like, well, I could have like a 10. And I'm like, no, 10 is 2 digits. And you're like, so where does it come from? Well, what else do I have besides digits? I got letters, right? So in fact, A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And so when I want to write some number in hexadecimal, I'll just write a number in hexadecimal because it's fun to write numbers in hexadecimal for about 2 numbers. And then it stops being fun. But just so you actually see it, 2B. You're like, yeah, over on the other side of the quad, this is Shakespeare. On this side of the quad, this is hexadecimal. What is 2B? It's base 16. What does that mean? That means this is the ones column. This in decimal would normally be the tens column. This becomes the 16s column. The next column, if we had one, would be the 256s column, etc. Okay? So if we want to think of this number, we have 2 in the 16 column, so that's 2 times 16 is 32. And we have a B in the ones column. Well, what's a B? That's 11. Okay? So we add 11 to that. So we have 1 times b, which is basically equal to 11. And what we get is 43. So 2b is actually the number 43 in decimal that we like to think of. Okay? So you might say, all right, Maron, that's great. Yeah, sure, whatever. Why are you telling me about this? And the reason why I'm telling you about this is when we think about the computer's memory, we think in terms of numbers that are hexadecimal. So a lot of times when you see memory drawn out, and I'll draw memory, because memory is so cheap these days, I can just draw it on the board. So we have a bunch of cells in the computer's memory. And each one of these cells is 1 byte. Which you know underneath the hood, what that really means is that cell contains 8 bits. Okay? And so each one of these cells has associated with it some location in memory at where it lives. You can kind of think of this whole thing kind of like the system of houses in the United States, right? How do you know where a house is, right? This little box is a house. How do I know how to get there? It has some address. It has some place that if I know its address, I know how to get to that box and see what's inside the box. And in the computer's memory, we refer to those addresses using numbers, and they're just numbered from 0 up until however much memory the computer actually has. So if you have 2 gigs, it's somewhere on the order of 2 billion, whatever that number is, except we write those numbers in hexadecimal. So somewhere in the computer, you have memory location A000, and that's just some box. And after it comes A001 and A002, all the way down. And somewhere down in the computer's memory, there's F, 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 F. And if your computer is large enough, it's got some more F's in there too. And it's in there. Trust me. You're like, oh, it gets a little, little scary now to use the computer. And up here, there was the very first address is 0000. But when we actually write these addresses, even though they would translate into some decimal value, we refer to them with hexadecimal. And the reason why we do that is we want to distinguish them as being addresses or locations of where things live in memory, as opposed to the actual contents of memory. Okay? So somewhere, yeah, at this location, there may be stored the value 10 in some binary representation. But we want to distinguish that this 10 is not the address 10. It's a number 10. It's an integer 10, whatever it may be. Whereas there's some address that we care about that's actually different. Okay, that's why we distinguish between these things. So when you're running your programs, where is all this memory coming from? Right? And it turns out there's 2 different sections. There's actually 3 different sections, but 2 that are mostly relevant to you, of where your computer actually says, hey, this person just declared an integer, or this person just called a method, or this person just created an object. Where am I going to get the memory to store all of the information that's associated with their integer or their object or their method call? Okay? And so the places where this memory comes from, and I'll show you all 3, there's some place where all of your static variables or your constants, you could kind of think of them if they're final variables. There's some special place that's set aside, so this is kind of special, right? Or if we want to get multicultural, it's especial, right? So it's special. And basically, we have static variables and constants that are just stored in the special location. Where is the special location? We don't really care. Okay? It's just our little lovely special location. Now, besides our static variables and constants, the things, because these, at the beginning of our program, it gets started, and all these things come into being, all of our constants, and they never change, which means they don't need to be in some portion of memory that we access regularly. They just need to be somewhere in memory that we know how to refer to them, and that's all. Okay? So we can have dynamic variables. And what are dynamic variables? Dynamic variables are just any variable that you use new on. Right? So when you say new, some object, like you say new G oval, and you pass it some parameters, that's a dynamic variable. And the memory that comes from for a dynamic variable when you do this thing called new is something called the heap. And the way you can think about the heap is it's just like a big pile of clothes. When you need clothes, you come along and you say, hey, I need some new clothes, and it gives you some clothes. And when you're done, you sort of just say, hey, I'm not wearing those clothes anymore. And somewhere magically down the line, when there's a piece of clothing that you stop wearing, the computer knows that you've stopped wearing it and it says, oh, I'm going to go take that memory back. That's called garbage collection. Wouldn't it be nice if there was like little gnomes or elves and like when you stopped wearing a piece of clothes and they knew you were done with it because you just had no way of ever getting back to that particular t-shirt again. They just went and threw it in the trash for you. Or they took it to recycling, which would be the more useful thing to actually do. Then that would be a form of garbage collection. Its memory from the heap just gets reclaimed when it's no longer being used. But as long as you're using it, so if you have some G oval object over here, which we'll just call G, as long as G is still being used, this memory is still set aside for you in a place called the heap. And I'll show you how the heap's kind of set up in just a second. Okay? So last but not least, besides static variables and these dynamic variables, there's another kind of variable that we care about, which are local variables. Okay? So local variables come from a place called the stack, to be differentiated from the heap. Okay? And the difference between the stack and the heap is that for the stack, whenever you have local variables in a method, or you also have parameters to a method, right? Those parameters, remember, you get copies of the values of the parameters, which means they have to live somewhere in memory. Some memory gets set aside for you automatically in this place called the stack. When you have your local variables and your parameters and your method is running, those variables are alive, and when those variables go out of scope, like the method actually ends, or you get some closing curly brace in which the cause of the variables to actually go away, the variables go out of scope in one sense or another, then the stack automatically says, hey, I'm going to take that memory back from you. Okay? So again, this memory, at least in the Java world, is automatically managed for you. If you come from sort of the C or C++ world and you're like, oh, how do I free memory? You don't worry about it in Java. It's taken care of for you. It's a good time. Okay? So what does this actually look like in the machine, in the computer's memory? Let's draw that over here. So where's the special memory, where's the heap, and where's the stack? It's kind of funky how it's set up, but you got to see it just so you can see what it looks like. Here's the area over here where all of our static or special variables are kept. Okay, it's just some section of memory. Usually this is some low area in memory. What that means is the numbers, the addresses here tend to be smaller, like let's say around 1,000, okay, which is actually 1,000 in hexadecimal, not in decimal. After the special set of stuff, we have the heap. And the heap grows. It grows downwards. What does that mean? That means if it starts at 2,000 and you say, hey, heap, I need some space for my new G oval, it says, oh, okay, well, I need to get you some more memory down here. Maybe this is location 2004. I'll get some more memory over there. And then you say, hey, I need a new G rect. It says, oh, okay, I'll get to location 2008 for your G rect, and I'll give you some memory over there. So the numbers associated with the heap increase, or what we refer to as the heap grows downward, because you can think of memory, the low values are over here, the low addresses and the high addresses are over here. There's something else called the stack, right, that we just referred to, so let me stop having the heap kind of take over the whole board. The stack starts off in the very high addresses. So here's the stack. It starts off at a place like FFFF, right, somewhere really with a really large value for its address. And as it allocates more memory, it grows upward, which means the addresses get smaller. And you might look at this diagram and say, hey, Meron, do they ever meet? And they do, sometimes. And if they do, it's real bad news. All right? So if your heap and your stack ever overlap, they start writing over each other. And usually what happens is your machine just crashes. But that's why you got so much memory. These days you're like, oh, I got a gig of memory. Yeah, because there's a billion data addresses between the heap and the stack. Usually not actually that much. In a program, they put them a little bit closer together. But you got so much space in here, it's just frightening. And you could probably use it in your program, right, by having some loop that just allocates a whole bunch of memory. But really, the thing you want to keep in mind is that these things, at least for the programs that, for most programs that you will ever write, you never have to worry about the heap and the stack actually coming together. Okay? So the one other thing that's associated with local variables, parameters, and dynamic variables, mostly actually with dynamic variables, is how much space gets set aside for something, right? And that's one thing you want to think about, is different kinds of variables actually have different amounts of space associated with them. So something like an integer, at least in Java, is 4 bytes. And this is not something you actually need to worry about, because it turns out on different machines, they may actually be implemented in slightly different ways. A character, it uses a special kind of encoding where most characters are actually in 2 bytes. Sometimes if you get into some very funky languages that have lots and lots of characters, or the way the special encoding for characters, the Unicode encoding, is actually set up, sometimes it can actually be as large as 4 bytes. So as far as you're concerned, you don't really care about the underlying numbers. It's an abstraction to you, and that's the key information, right? Even these little things like an integer or a car is just hiding information. It's hiding the fact that it's a bunch of ones and zeros underneath the hood, and you don't need to worry about it or how big it is. All you need to know is how to use it. Okay? So along with that, with dynamic variables, there's also a little bit of overhead memory. And it's just an extra amount of memory besides how much space is taken up by like your integers or your cars or whatever variables are inside your object to keep track of other information about the object. And how much information is actually kept track of in that overhead is not important, but it's just important that you actually know that there's some overhead associated with it. So putting all this stuff together, it turns out that we can look at the mechanics of what actually happens underneath the hood when you run your program and you create new objects, right? So if we go to the slides for a second, let's actually see sort of diagrammatically what's going on when we actually create new objects and declare variables, okay? So what we're going to have is some class called a point. And this is a super simple class. All it does is you can create a point with its constructor by saying, here's an x and y location. And all it's going to do is store an x and y location for you and let you move them around, right? It's real simple. It's something you can imagine might be convenient to have when you're doing graphics. So you pass it an x and a y. It sets its own internal instance variables, px and py, which I just called px and py to remind us that there are private x and our private y that are inside this particular class. And then there's another method called move that you pass at some offset in the xy location, and it just changes its private x and y by whatever offset you give it. Okay, fairly straightforward. Should be pretty easy to understand given all the stuff you've done with graphics so far. And then we can say, okay, you have this class. You haven't done anything with the class yet, right? We've just said, hey, I have this class. No memory's been allocated. Nothing's actually been done. What you're going to have is some program somewhere, like my program, that's going to come along and create new points and call methods on those points. And we want to understand what's actually going on in the computer's memory when this happens. Okay? So everyone happy with the point class? I'm going to make it disappear in just a second. Can you remember what it does? There's two methods. There's the constructor and the move, and then there's two private variables, px and py. Okay? So let's see what happens when your program's actually running. Okay? Now, just as a little mnemonic, we have the heap and the stack. Heap is going to grow down, stack is going to grow up, just so you can see that as we go along. And the first thing we're going to do is our method run gets called, right? When your program first starts up, the method run gets called. What happens when a method gets called? Well, when a method gets called, we create all the local variables and parameters. Run has no parameters, so we don't need to set aside any space for parameters. It does have two local variables, p1 and p2. So space, notice this is starting at the very bottom of memory, like FFFF. There's some overhead for the fact that we create a method, and I just sort of blocked that off and called it overhead just to match sort of the same style that the book does it in. And then there's some space, some number of bytes, and in this case I just said 4 bytes, that get set aside for P1 and some number of bytes that get set aside for P2. Right now they don't contain anything because my program's just started. I haven't gone to this new point stuff yet. All I've done is said run. So it says, oh, okay, you have some local variables. I'm going to set aside space for your local variables. Now what are you going to do? I'm going to say, well, I want to create that first point. I'm going to call new. If I'm calling new, that's going to be a dynamic variable, which means it's going to come from the heap. So here's what happens. I call this line. I say p1 equals new point, 2, 3. So it says, hey, you're calling new. You need some new memory. That's dynamic memory. I need to get it for you from the heap. Where does the heap start? The heap starts up at the top and goes down. What data is associated with a point? What values do you need to store to actually keep track of a point? Well, a point inside it has its private x and its private y. So I have to set aside space for everything that a point encapsulates, which includes all of its private variables and its public variables as well. But all of its instance variables get space allocated for them. And there's some amount of overhead associated with the fact that we need to keep track of some extra information about this point object that you don't need to worry about, the computer needs to worry about. So there's some overhead. Let's say there's 4 bytes for that, 4 bytes for the integer px, and 4 bytes for the integer py, which is why you can see memories growing from 1000 to 1004 to 1008. So each one of the boxes up here is not 1 byte. I've just kind of stylized it to make it easier. Each box is now representing 4 bytes because integers are 4 bytes and the amount of overhead we're keeping we're just going to say is 4 bytes, although you don't need to worry about that. Okay? And what did we do when we called the constructor? We set the private x to be equal to the value 2 that got passed in and the private y to be equal to the value 3 that got passed in. So that all the constructor did was it wrote into the little places for px and py, which means it wrote into the memory locations that the computer set aside for it the values 2 and 3. Okay, any questions about that? The 1000, sorry, is on the, oh, excellent point. Why is there a 1000 over here? Because the one last thing I didn't actually mention is after we've set aside the memory for the new point, what are we going to do with that point? We're going to assign it to P1. So here's the critical concept. How does the computer know where P1 and all the information associated with P1 is? every object lives at an address. The way the computer actually is referring to objects underneath the hood is by the address at which they live. Okay, so you could think of, there's some little house over here that's P1's house, and there's like the little kids in the house, PX and PY. They're like, oh, we're the little children, we store integers. And then I say, well, how do I know how to access you, P1? I need your address, which is 1000. That's where you live. So when I do this new and I create the memory off the heap, it says, hey, I'm going to assign that thing over to P1. What's the thing that you're actually assigning? You're assigning the memory address for where P1 lives, or its starting address. And from the starting address, we can find everything that lives in P1. So what's getting stored here, this value 1000, is not an integer. You don't want to think of it like the value 1000 that's an integer. You want to think of this as the memory address 1000. Okay? Overhead. So that little overhead gives additional information that it uses to keep track of stuff. So how do we do the next line? Okay, very similar kind of concept. We say, hey, I'm going to create a new point. Oh, heap, I need some more memory. And so the heap says, okay, well, everything up until 1008 was allocated, so I'm going to give you some more space in memory that's enough space to store another point, which means I'm going to give you space for your instance variables, px and py, and your overhead. Notice this px and py are distinct from that px and py, because this is the px and py that are the instance variables of p1. The second px and py over here are the instance variables of p2. They're distinct things, so they have separate memory to store them. Okay? And same thing, when we return a value that we're going to assign to p2, what we're going to assign is the address that's the beginning of the space that we set aside, the memory that we set aside for p2, and that's at 1000C. So 1000C gets stored there. Okay? Any questions about that? It's basically the same thing, except you can see the heap is growing down. All this memory's already been allocated, so any new memory we need requires the heap to keep growing downward. Now, next funky thing, right? We're going to do a method call. So we're going to say p1.move. We're going to do a method call. When we do a method call, what ends up happening is we're going to have some parameters and some local variables, which means we're going to have to allocate some memory on the stack for that method call. So when we start the method call, what ends up happening is we say, hey, P1, I want you to move yourself by 10, 11. So what actually happens in memory? What happens in memory, starting at this point upward, is we create a new stack frame. Remember when we talked about stack frames, we said when you call a method, it's sort of like the previous method or previous place you were running just gets suspended, and we sort of create this new frame on top of it that contains all the information. We drew little boxes for the variables and all that when we did stuff like tracing palindromes and all that happy news. Remember that? If you remember that, nod your head. Right? Yeah, what was going on underneath the hood? It wasn't just nice, I mean, at the time it was nice pictures. This is what was going on underneath the hood. Some memory was getting created on the stack, and that's why we refer to this as a stack frame. It's keeping track of that frame of information for the method call, and it does it on the stack, which is why it's a stack frame. What information goes on the stack frame? Well, you get some overhead for the fact that you're calling a method. So there's this overhead is this first 4 bytes here. Then you get all the parameters that you're passing to the method. And you might say, but Maron, the parameters I'm passing to the method are dy and dx. What's this thing all about? Okay? There's a hidden parameter that you didn't know about until now, and now you know about it. When I'm calling a method on a particular object, how do I know which object, once I'm actually getting into the details of things, I actually called the method on? And so when you make a method call on an object, the very first thing after the overhead that gets put onto the stack is essentially a pointer to the object, right? It's what we refer to as the this pointer. Remember when we talked about the this pointer and we said this is basically a way for an object to refer to itself when it's been called? Well, how does it know how to refer to itself? It needs to know where itself lives. And you might say, that's kind of weird, Maron. Why does an object need to know where it lives itself? Because when I write some method, these methods are not yet associated with particular objects that I created. Once I create particular objects and call that method on them, this method over here needs to know, hey, when I'm doing these modifications on px and py, which px and py are you referring to? That's where this comes in. This says, hey, I'm going to tell you the place where the particular object lives whose method is being called, so whatever modifications you make over here, you know to make them to the object that lives at this address, which is why it's called this. Okay? So when you make a method call, the first thing you get is the address of the particular object that you're making the method call on, right? We're making a method call on P1, and P1 lives at 1,000, right? So P1 is just 1,000. So this is the value 1,000, and then I get the parameters in reverse order because the stack's growing upward, right? So I get dx first, then I get dy. And those just get the value 10 and 11 that are passed into them. I get copies of those values, okay? Any questions about the this pointer?
I guess I had a question about graphics variables. And when you add like a geoval to the screen or something, is it a dynamic variable or is it a local variable? If you add it to the screen in a method and then it's still on the screen in a different method.
Geoval is going to be a dynamic variable because you called new on it. So anything you say new on is a dynamic variable.
Then why is point a local variable?
Because what's going on here is that P1 is just the address of where the actual stuff lives. All the data associated with that particular object, P1, is on the heap. Okay? So P1 is a dynamic variable, right? The place P1 where I store the address, where the place I keep track of its address to know where to look it up, is something that is local. So I keep track of P1 by itself as being local. The actual object itself that's created when I do the new is on the heap. Does that make sense? So the address is a local variable. So when I say point P1, all I'm getting is an address. When I do the new, that's when I'm actually saying, hey, set aside space for a dynamically created object and let me know where it lives. So yeah, there's a subtle distinction there, but the important thing is that the variable itself, just the address, can be a local variable, but the actual object itself is the dynamic variable.
Do all the different parameters that you, or all the different messages that you could possibly pass to, like, say, a geoval get stored on the heap? Or, would the set field be just false by default? Would that actually go on the heap? Or is there nothing that's put there until you actually send something to it?
So you would need to know all the internals of geoval, and geoval does actually keep track of an internal variable for whether or not it's filled, right? So when you create an object, whether or not you set its variables, those variables all need to have some initial value that the object's going to set itself if you don't set them. So they're all on the heap.
So if you're doing some sort of like an integer declaration, like you're saying int x equals like 10 or something, do you get like something on the stack for like where x is, and then you get like 10 in the heap?
No, so ints, that's the funky thing, and we'll get to that in just a second. Ints, doubles, characters, and booleans are different than objects, right? So when you use ints, doubles, and characters, you never say new. So if you don't say new, it's going to show up only on the stack. Things that you say new on are the things that show up on the heap. So all of your basic types of variables like chars and booleans and ints and doubles, those, when you declare those, you never said, hey, I need a new character. You just said, hey, char ch, and you got a character ch. That was all on the stack. The only time you actually created something on the heap was when you said new, like you said, hey, I want some new grect. Then you actually got one on the heap. So let's keep following this through and see what happens when we make this move call, right? We got all this information on the stack. We haven't actually done any of the instructions in move yet. So move comes along and says, hey, I'm going to do the first instruction. I'm going to add whatever is in dx, which happens to be the value 10, over to px. Which px do I know to refer to? It's the px that I get to by following the this pointer, or going to the address of this. So it goes up to 1,000. It looks at the overhead, and so it can figure out where px is, starting at location 1,000. And it says, hey, it's over here. Its value was 2. I add 10 to it, so now it gets the value 12. Okay? And it does the same thing on the next line when it's modifying py. It says, I want to modify py. Which py am I referring to? The one that's at location 1,000. So it goes to 1,000, says, hey, where can I find py from starting at 1,000? It's over here. And it adds 11 to the value 3 that was there before, and I get 14. Okay? Now this method is done. Right? The move method, we executed everything in the move method. It's done. Here's the funky thing. Remember, I told you, when a variable that's on the stack goes out of scope, when it's no longer being used, the computer automatically comes along and says, hey, that variable, that memory's not getting used anymore. I'm going to take it back. So all the memory over here on the stack that's associated with the stack frame for the move method, right, which is the parameters to move, the this variable, which is actually sort of a hidden parameter to move, and the overhead associated with move, that was all the memory that got allocated when I did this move method. This move method is now done, which means all of the memory that's allocated just to execute the move movement automatically gets deallocated by the machine. It's what we refer to as popped off the stack. Because if you think about the stack growing and we get to a certain point and we're like, hey, we're done with this top part of the stack, we sort of say, boink, and we pop it off the stack and it goes away. So when we pop it off the stack, moment of silence, it goes away. Right? And then the program just keeps executing from wherever it left off. Right? If there's another method called, guess what? The stack's going to now grow from this point. Okay? So any questions about that? If we were to call the move method again, it would recreate all of the stuff it needed on the stack for another invocation of move. Because all that stuff's temporary, right? After it does move once, it doesn't need it anymore. If you invoke move again, it'll create it again. That's just the way life is. All right? So any questions about that? Now, one thing to keep in mind that's important is that there's a duality here, right? I keep referring to this thing called the pointer. So I will just whip out the pointer, right? Think pointer. It's like, pointer. I always feel like a little evil when I actually hit the board with a pointer. But the way to think about the pointer is, right, this thing's the value 1,000. Really, this is referring to address 1,000. This is just kind of pointing up to 1,000, right? We don't really care what the value was in here. All we know it's some memory address up to 1,000. So what are we going to do? Let's just draw it that way, okay? So rather than having this thing write out 1,000 in here and remember, oh yeah, that 1,000 is supposed to be a memory address, etc., we can just draw it as a pointer and say, yeah, this thing is really some memory address, and the memory address is just pointing over here. Yeah, this 1,000 over here lets us know that it's 1,000, but graphically it's a fun way to keep track of it, like for some definition of fun. It's a fun way to keep track of it because then you know that you're not going to muck with this variable in here as though it were an integer, right? This thing is just some referring to some piece of memory where you're actually storing some object. And similarly, so is P2. Okay? So that's what we like to think of as the pointer viewpoint of the world, right? It's just the fact that things that are memory addresses are really pointing somewhere. They're telling the machine basically like, look, I know where you live. Let's do another one real quickly, okay? So another memory allocation example, here's again our point, right? Same point that you just saw, except I've left off the move method, and now I'm going to create something called a line. And a line has 2 points associated with it. So when I create a line, I pass it 2 points to its constructor, right? 2 things of this object. And it has a line has a beginning and an end, which are private points that it keeps track of. Okay? So I say, hey, beginning is going to be the first point you give me, end is going to be the second point you give me, because Euclid told me a long time ago that a line is defined by 2 points. So if I know those 2 points, then I know what the line is. Okay? So what's going on if we actually think about this in the computer's memory, if we want to try to create 2 points and then create a new line? Okay? So everyone's sort of clear on points and lines. They're just 2 basic classes just to kind of illustrate the point. Haha. Yeah, not funny. So when we actually create the 2 new points, we get exactly the same sort of diagram we had before, right? We have memory allocated on the heap at location 1,000 for point 1 and 1,000C for point 2. The other thing we have is in this version of the run program, we have a local variable called line, which I've just abbreviated ln. And so we've gotten some memory allocated for it over here. Notice it doesn't have a value yet. It doesn't have a value yet because we haven't asked the heap yet for the new memory that actually stores all the information for that line. All we've done is say, hey, you know what? I'm going to have some local variable called line in here. When you get to the new line over here, then you're actually going to ask the heap for memory and things are going to get set up. So let's see what happens when that line gets called. Okay? We're now going to go into new in excruciating detail. When we say new, before we do any kind of assignment over here, so this still remains blank. When we say new, what it does, it says, hey, I'm going to go over to the heap and I'm going to allocate space for a new line. What are the variables that are part of a line? There's 2 variables, a beginning and an end. Okay? And they're both points. I haven't initialized them yet. I'm going to actually go into the details of the line constructor in just a second, but it sets aside space for you for its variables, which are beginning and end. Now, we call the constructor method. So actually, I didn't show you this before when we did it for points, but what was actually happening when we called the constructor is the constructor is just a method, just like any other method. So what happens with this method? Except the constructor doesn't have a this pointer associated with it because it hasn't created the object yet. It's still in the process of creating the object. What it does have, though, is it has the parameters that get passed into it. Well, what are the parameters that get passed in there? P1 and P2. What are P1 and P2? They're pointers. They're just values that happen to be memory addresses. So what I do is I pass a copy of the address 1,000 and a copy of the address 1,000 and C. And I don't create new versions of P1 and P2. All I do is I pass copies of their addresses. Okay, are we clear on that? That's the critical concept here. So what happens after that? This guy comes along and says, hey, set beginning to be P1. Well, what's P1 that got passed into me? It's 1,000. So it just sets beginning to be 1,000. And then the next line comes across and says, hey, set end to be P2. Well, what's the P2 that got passed into me? It's 1,000 in C. So it just sets end to be P2. And then it says, hey, I'm done. I did my work. I'm the constructor. I did the 2 lines you told me. So it's done. And all the memory that's allocated with this particular method call, which are the 2 parameters and the overhead that's associated with calling this method, all get popped off the stack. So they get popped off the stack and they're gone. And now we say, hey, thanks line constructor. You just created a, first of all, thanks new. You allocated the memory for us. Thank you, line constructor. You went ahead and initialized all the fields that I needed for a line. Thanks a lot. What do I do with that now? And it says, yeah, what I need you to do is assign that object where that object lives to the variable line. And so the variable line, which is over here on the stack as a local variable, finally gets assigned the address of the line object on the heap, which is at 1,018. So when the whole line executes, basically what it's done is it's called the set aside memory with new, called the constructor, had the constructor fill in the initial values, and then what actually gets assigned to line over here is the beginning memory address for this object that was allocated on the heap. Okay? Any questions about that? Now here's the funky thing. Let's take a look at this in the pointer viewpoint of the world, right? So the first thing we could do is say, hey, let's look at the pointers over here, right? These are all pointers. This points over to 1,000, this points over to 1,000 in C, this points over to 1,018. So we could just draw that looking like this. But we're not done with all the pointers, right? There's still more pointers left. Guess what? Beginning and end, they're just pointers back into the heap, right? Beginning, it just says, hey, the point that you gave to me is just a point that starts at memory location 1,000, and end is just location memory 1,000 in C. So really, these guys are also just pointers back to the respective locations to those particular objects. Okay? Any questions about that? I know that looks kind of funky, and the reason why I did it in slides as opposed to on the board is because I want to post the slides so you can refer to them back after class if there's any questions. But that's the funky thing. You can actually have things on the heap that refer to other things on the heap. Okay? Uh-huh. Well, you need to convert it to decimal, right? It's just a hexadecimal number. And you don't care what the actual value is. All you care about is that it's an address. It's not, a number that you would manipulate like an integer. We can talk about that offline. I mean, it's easier, as far as the book's concerned, to be able to do differentiation, to differentiate between addresses and non-addresses, but there's also some history to it in computer science. So I just want to show you one thing very quickly, and then I'll give you a quick video. So if we have point P1 equals new point 1, 1, and then we have some point P2 that equals P1, what's really going on in the computer's memory, right, is P1 is just some address somewhere, and this is on the stack, and P2 is also just some location that's also going to be an address because it's just an object. Now this is the stack. Here's the heap over here. When I create P1, I sort of create some space over here that's going to store a 1 and a 1, and there's some overhead down here that I don't care about. And this guy's going to point over to here. Let's say this is a memory location A, B, C, F. Okay? It's just some memory location. When P2 comes along and I set P2 equal to P1, it just gets the same value as P1. It gets A, B, C, D, F, which means this guy's pointing to the same location. Okay? So if that's the case, then if I do something like, say, P2.move 10, 10, what happens there, it says, hey, I'm going to go and move based on P2. Well, where is P2 pointing? It's pointing over here. It's pointing the same place P1 is. And it says, oh, I'm going to move it by 10, 10, so I get 11, 11. And you might look at that and you say, but Maron, you just changed P1 without ever referring to P1. Yeah, if you have two objects that are pointing to the same place because you set them equal to each other, what you've done is set their pointers, not created copies of objects. Okay? That's why it's sort of like you're old enough to know what's going on now, right? Before we just said, hey, every time you just create a new one and that way they'll all be distinct. If you don't create a new one and you set some local variable to be equal directly without doing a new, notice I didn't do another new point here. All you're doing is setting their pointers to be equal to each other. Which is why in the days of yore, when we talked about our friend the string, remember the string, and we said if you had some string s and this was equal to hello, and you might want to say, and this was s1 and I had some other string over here, s2, and this was also equal to hello. And I might want to say if s1 is equal to s2, and I told you, yeah, this doesn't work because you need to call s1 dot equals s2. The reason why it didn't work is when you check for equality here, it's not checking to see if these strings have the same characters. These strings are objects. They have memory associated with them. When you check to see if the actual objects are equal to each other, it's looking to see, are they referring to the same actual thing underneath the hood? These are not. These have two versions of hello in different places in memory. One's over here and one's over here. So S1's a pointer or S2's a pointer here. S1's a pointer here. These guys are not equal to each other. They would only be equal to each other if they were in fact the same object, and I'd set S2 equal to S1. Okay? So any questions about that? Alrighty, so if you want to go, you can go now. And if